Hello, this is a video which would be speaking mostly on work done. Now, as you have noted in this work done video, I have mentioned 4 points which we would be speaking on this. First is a general definition of work done. What is work done? Then we will look into the variable forces that contributes to calculating work done. We will third look into on an inclined plane, that is when we are getting an inclined plane, what is the way in which we can calculate work done. And fourth is that multiple forces, when there are multiple forces which is acting on a body, so how we can calculate the work done. So let us start with that. First, initially we will look forward for a very simple example where we would involve two components. One is force, and obviously when it is moving it would be displacement, and we are going to look forward that how it is going to happen. So let us start with the initial example, that is how we can measure something like this. Now let me give you a very simple example. Say for example this is a person, right, and he's standing over here, and this person has got a book in his hand or any object, right, and he's lifting this object. This object is lifting up to a height. It is going up here, and what we are doing is that we are measuring from here. The height which has happened is around 40 centimeters, right? So this is a person who has got a book in his hand, is lifting at around 40 centimeters height. So what would be the work done? Now in general we know that the formula for work done is force multiplied by displacement. So we can put it as force multiplied by displacement. That is amount of displacement which has happened. Now for example, it is given from here that the force is 40 newtons. Okay, so we can put it simply as 40 newtons multiplied by the displacement, which is given as 40 centimeters. So I can write it as 0.4 meter, because I want to convert it to a SI unit, because force unit is in meters, Newton. So I will make it to 0.4 meter, but this is 40 centimeter, for example. Right, so what we can do is that we can multiply this, and what we get is around 4 Newton meter. So we get this one as 4 Newton meter. And this Newton meter, we have a unit which we have spoken in the earlier video, which is called joules, right? So the displacement or the work done which happens is 4 joules of work. So I can mention here this one as 4 joules of work. This is the very basic idea, and we just started with the initial demonstration. Here is a person who has got a book in his hand, lifting to a height of 40 centimeters, which we convert to meter, and finally we get 4 Newton meters, which is 4 joules of work. Now what happens if the force, so what you see is that the force and the displacement are in direction. So the force is in this direction, right, up, and the displacement also happens in this direction. So I can demonstrate something like this. If I got a pen over here and I've got my finger, let me show you. Yeah, if I got a pen over here and it is my finger and I am moving this, there is a displacement which is happening. So this finger is my force which is moving the pen in this way, right? So this force and the displacement is in the same direction. Now let us take an example where the force and the displacement is not in the direction. You can imagine a kind of a object which is being pulled over by a string. So let me show you one example how it would be. So say for example we have an object over here, right, and in the earlier case the force was this, displacement was this. Now what is happening, that the force is in this direction, okay, and the displacement happens in this direction. In this direction. So I've got a knot tied to this and I'm pulling it. So the force and the displacement is not in the same direction. It is happening in this direction. This body is being pulled. So this is where the displacement happens. I can put it as displacement. Right, this is where the displacement is actually happening. So what would be in that case? So let us take a simple example and let us see if we can work out on that. So force, say for example, if I draw this figure, it would look something like this. So it would be something looking like this, right? So what is happening over here is the force is along the hypotenuse. The force is along the hypotenuse. The angle theta is between the force and the displacement. Which is the angle? This is the angle theta, right? This is between force and displacement. This is the angle, you see this one, so this is the force. So it is pulling over here, an angle is getting created. So what would be the component of the force? Now this angle is cos theta. So why? Because cos theta, if we've gone through the basic trigonometry, we know that this is base by hypotenuse. So it would be base by hypotenuse, right? So in case that you have got an object something like this and you're pulling this object in this direction, so it creates an angle. We've got an object like this, it is pulling in this direction. So what we get is cos theta. Cos theta is base by hypotenuse. So in that case, what would be the work done? What would be the work done? It would be the force we have seen over there multiplied by the angle which is over here. So we get F cos theta, right? Multiplied by the displacement. So we measure it as S. This is the displacement. This is the angle. And this is the force. Comes quite simple. So we've got an object, we are pulling in this direction, it is getting pulled, it is getting displaced in this direction. So it would be F multiplied by the force multiplied by the angle, that is cos theta, and then we get the displacement. So now we can write very well that we have understood till now two formulas. One is F. We can first formula is what? W equals to Fs. This happens when the force and displacement is in the same direction. Force comma displacement in same direction. So we have seen that in the earlier example, that the force is in this direction, displacement happening in the same direction. So we use this formula Fs. What we have learned from the second formula is that W equals to Fs cos theta. I rearrange that. So it would be Fs cos theta. Why cos theta? Because force and displacement is not in same direction. Is not in the same direction. So that is why it happens something like this. So these are the two formulas. I believe it is going quite clear. Now for example, let us see another demonstration. In this case what I will do is that let me draw a figure. Let me draw a figure over here. Say for example this is a body, a book, anything that you want to imagine, and we have got a force applied over here, right? Now this body is moving and it is coming over here. So obviously there is a displacement, right? It has started from here and it has moved over here. Now you see that there is no angle involved in it. There is no angle involved in it. So angle is 0. So we can write here the angle equals to 0, right? But what is that cos theta? What is 0? Like we can use this cos theta. So we can always write cos theta equals to 0. So angle displacement is 1. And what is the value of cos theta equals to 0? It is 1, right? It is 1. So what happens is that in this case, the work done that we get is Fs. The Fs, that is the first formula, because this is 1. Cos theta is 1. So we got back to this one. You see, force multiplied by displacement. I didn't mention deliberately the angle part because we learned in the second part. So now when we use this angle, it becomes 1. So effectively the answer is the same, isn't it? Effectively answer stands to be the same. So it is Fs1. So that is the value, that is the work done which we get. Now we are coming to another example. Now, for example, if we take something like this, say for example, if I draw a demonstration where we see a person, okay, let me write. Okay, let me draw something like this. Yeah. So in this case, what we are demonstrating is that we got over here a person, okay, right, and this person is carrying a bag. Say for example, this person is carrying a bag. So this is a bag, and this person is moving in this direction. This person is moving in this direction. So there's a displacement, right? So in that case, what will happen is that what is the work done if we are if it is moving in this direction? Now, if this person is holding a bag, right? So the force would be, if it is carrying a weight, so the force would be in this direction, right? So this would be the force. And the angle formed between these two, that it is moving in this direction, carrying a force. See, the angle formed is 90 degrees. The angle formed is 90 degrees. So if it is angle that is formed is 90 degrees, let us find out what is the work done. So as per the formula, we go ahead and what we do is that we calculate the work done. We calculate the work done as we put it as Fs cos theta. Right? But cos theta here is 90 degrees. So we can, and what is cos 90? Cos theta, if it is something like this, cos 90 degrees equals to 1. So Fs, this is just 1. Multiplies, I'm so sorry, cos 90 would be 0. I'm making a mistake. Cos 90 is 0. So Fs multiplied by 0, and this comes to work done equals to 0. Let me rewrite this. Cos 90 degrees equals to 0. So the entire equation goes down to 0. That means that work done is 0. How can it be possible? So you need to understand one concept over here, that when he is walking along the path, this person is walking along the path, he is doing a non-zero work. He is not doing any work. It is a non-zero work against the force of friction. It is a non-zero work against the force of friction, hence his work done comes to 0. We will deal more about friction when we are doing the next video, so we will understand why the friction is taken into account. Now let us do another example, and in this case what we will show is that this person, see okay, I mean, yeah. So for example, this is another case where we have got another person standing over here, right? And this person has got a book, something like this, is holding the book, right? This is the object, right? Displacement happens in this direction. It is displacement happen in this direction. However, note that the earth is pulling the book downwards, isn't it? So it is in the opposite direction. So this is gravity. It is pulling down, and this is the displacement which has happened. It is moving up. This is the displacement which has happened. Now, how can we calculate the work done over here? Remember that the earth is pulling the book downwards and the displacement of the book is happening upwards. That means it is in opposite direction. So we need to understand that this angle which is being formed, this angle is 180 degrees, right? We have seen earlier, say for example, let me show you this. If this is one, and if this angle and this angle, which is a ray or a straight line, this angle comes to 180 degrees, right? So in this case, what is happening is that the angle formed is 180 degrees. So immediately from here, what we can see is that we need to find out the cosine of 180 degrees, and we know this is -1. Cosine of 180 degrees is -1. So in that case, what we will do is that if we write down the formula of work done, that is Fs cos theta. So we get it Fs cos theta, right? So Fs, we haven't mentioned any force. He's just holding the book. The displacement has happened in this direction. He's just holding the book, and the earth is pulling for it downwards. So what it will happen is that we will get Fs multiplied by -1. because cos 180 degrees is minus 1. So this is basically a negative work which is being done. So we call it negative work. So in this case, we got a negative work which is being done. So the work done is negative since force and displacement are in opposite direction. The force is in this direction, the force is in this direction, this is the force, right? And the displacement is in opposite direction. That means that if you are eventually standing on, if you're standing somewhere, and if you're throwing a stone, say for example, if this person is standing and just throwing the stone upwards, the force is in this direction. He has thrown the force, but the gravity is pulling downwards. So in this case, it would be a negative work. So I think we are going nice and fine. So let us quickly summarize what we have learned till now. We have learned what is the definition of force, and we have done 3 ways in which we can write the force. So let me write it for you. So the first one, what we have done is that if theta equals to 0 degrees, that is that the force and the displacement in the same direction, then we use this formula W equals to Fs, right? For the second case, we can write that if theta equals to 90 degrees, right, it is perpendicular, then obviously the work done would be 0, right, because cosine of 90 is 0, right? And also what we have seen recently, if this theta is 180 degrees, then the work done would be minus Fs, that is a negative work done, right? So let me just quickly show you what we have done. So we started with this. I'm sorry for the dots which has happened. So we have seen first that the force and the displacement is happening in the same direction. So we use this formula W equals to Fs, and we can calculate the force which is being done. If the force and the direction forms and the displacement forms an angle, then we use this formula Fs cos theta, and we get this one. So we find the theta value, that is cos theta base by hypotenuse, we get it. If the force and the displacement is moving in the same direction, there is no angle which is being formed, so we find it that Fs equals to 1. We have shown another example where the force is in this direction, person is moving in this direction, so cos of 90 equals to 0, so there is no work done. In case if it's throwing this up, or if there's a displacement in this direction, earth is pulling it in this direction, what we get is cos 180 degrees, which is minus 1, and we get a negative work. So 1, 2, 3. These are the 3 work done which we have learned in the first part of the video. Well, we go to the next part, which I would say is something we called it work done by variable force. Now, okay, let me just rearrange my papers so that it becomes visible to you. Yeah. Okay, I think this is quite visible, right? So work done by variable force, I will make you understand one by one what is the graph. Now you see, in general, in the real life, work done and the force is not in the same way. That means you're pushing and things are moving. No. What happens is that the force that we apply on an object, it takes a kind of a graph, it takes a kind of a variable, it moves in this way. It's not always the same. These 2 graphs are similar to each other, right? But I will come to the point why I have explained this. Now, for example, we have an object starting from here, and it has moved here, so we have mentioned this point as A. This is the force, which is a function. I have mentioned it as Fx. What we are going to do is that we are going to take the work done in this particular area, from here to here to here, and then it is coming to this part, right? So PQ RS is a tiny strip, which this PQ is very small. It is extremely infinitesimal small. Right, so force is always variable in this case, because that is why it has formed this kind of a graph. Now let us see if we can calculate this part. So the distance is changing. So what would be the work done in this particular? So let me just color it. So we find it like this. We are concerned about this one, this tiny strip. So what we write over here, that is work done, W equals to this one, PS, that is the straight one, right? Multiplied by PQ, this is the displacement. So this is the force which has been applied, and this is the displacement which has happened. So PS multiplied by PQ, right? Okay, so this is basically representing, this area. This is basically representing the area. So we can always write W equals to PS PQ. Yeah, PS. I'm so sorry. Yeah, PS PQ, which is again equals to the PQRS. It is the area of this. So we write as PQRS. That is the area. We are concerned with this part, right? Now, to calculate work done from a variable force, because this is varying, we obviously have to use calculus and we need to integrate, because we need to find the sum or the integration of this particular part. Very simple. What we can do over here is that we can write W, that is the work done we are calculating. It is the integration of say for example 2 variables. So I put it as x1 and on the top I put it as x2, right? And we have mentioned this as the function of x, so we can very well write it as f of dx, f dx, right? So it is an integration because we have to sum up this part, which is this strip, and we have taken two variables, x1 to x2, that is the limit, and this is a force. So let me write it for you. This would be the force, and this is the displacement, right? This is the displacement. Infinitesimal small displacement, and that is why we have differentiated using dx, right? So from x1 to x2, that means that work done by variable force is the area of the force curve to displacement axis. Area of the force curve to displacement axis. If you see this in this graph also, what we have done is that we have taken this, I have magnified this and I have made it this. So we are basically calculating the area under this graph, and this is what we are calculating. We are calculating the work done over here. We are calculating the work done over here. So I've just magnified and showed it to you. Now, for example, in order to understand things better, say for example, if we take, let me cite you an example. Say for example, we are given a function, say f of x. Okay, f of x equals to 5x Newton. Say for example, 5x Newton. Okay. Now, why I'm showing you is that it actually means that if displacement is 1, the displacement, if say for example, if I make the displacement is 1, then the force would be 5 multiplied by 1, 5 newtons. If the displacement is 2, and my force would be 10 newtons, right? 5 multiplied by 2. So this part is varying. Now let us see that if that is so for displacement of x to say 2 meters to 5 meters, if I take a limit from 2 meters to 5 meters, can we find out the work done by using this integration? So we write over here W equals to, I take the integration from 2 to upper limit of 5, from 2 to 5, right? And I write 5x dx. So we write 5x dx, right? From here, what we can write is that if we solve this integration, 5 will come outside, and we can write something like this. The x would go on the top, so x squared by 2. I take the limits on the top, upper limit, lower limit, 5 and 2. This would lead to 5 by 2, and this is 5 squared minus 2 squared, right? So if we solve it further, we get, this would be 5 by 2. This would be how much? 25 minus 4. It would be 21, right? So 21, right? And if we further solve it, this would lead to 105 by 2. This would be 105 by 2. And eventually it will come to 52.5 joules. So this is how we can calculate the value of work done in a variable force. Simple, quite simple. Just we have to use the integration. Now obviously I just need to mention one thing, that displacement should be 2 to 5 meters. What is the limit that I have taken over here? The displacement, that means I can write over here x would be 2 meters to 5 meters. 2 meters to x equal to 5 meters. 2 meters to 5 meters, 2 by 5, right? And that is why we have written this one. And I have taken an integration from 2 to 5. This is the lower term limit, 5x dx, that is the differentiation part. So from here we get this, and from here we get this one, and we get the value that is 52.5 joules. So I think it is pretty clear. I have shown a very, very simple example, work done by variable force. In general, it is always work done is variable because it moves in this direction, right? It goes in this direction. This is a magnified one. So if you are involved in calculating the area of this, that is PQRS, x to x2, it would be a function, it would be dx. If you are given a function of x, force as a function equals to x, this would be 1, 1 will become 1, 2 will become 10, 3 will become 15, so on. Work done, if you want to calculate through integration, so what we get is this. Provided that x is varying from x 2 meters to 5 meters, and by calculating we get this part. Right, so this is how we can calculate work done in terms of variable force. Now let us see a very simple example in how we can calculate work done on an inclined plane. And I'm not going to make things complex. What I'm going to do is just I'm going to use a right angle triangle. So that will make life easy. So let me draw over here. So you see this is an inclined plane, right? Okay. So and what we do is that we use there is a mass which is sitting here. Okay. Sorry. Yeah, this is a mass which is sitting over here, right? And it is eventually going to slide down and is going to come here. So for this mass, I'm just putting in dotted line so that you can understand that it is coming over here, right? This is a mass which is M. This is a mass which is going to slide down, right? Okay. So now what we need to do is this the work done. Now see that the force, if I draw it in this part, so what we get, this one is 90 degrees, right? This one is 90 degrees. Now this one is cos, this one is theta, this one is theta. This is going to slide down over here. So what is the work done that we are going? We know that this if it is coming down, then there's a force which we just learned that which gravity is pulling down. We call it as mg. So what is the element which is going to happen in this direction? If this angle is theta, this angle is 90 degrees, then what is going to, and say for example, this is the displacement which has happened, I take it as L. So, and this is the force of earth which is pulling downwards, right? So what is this going to happen? Obviously, if this is theta, this is 90 degrees, then this would be cos 90 minus theta. Yep. So it would be cos, this angle which would be here. So I will just put it as cos, yeah. So it would be cos 90 minus theta. Cos 90 minus theta. What is cos 90 minus theta? It is sine theta, right? Simple. So from here we have already got the angle. So we will just substitute the values and we will get the work done. It's quite simple on an inclined plane. So let me write the old formula which we have learned. It is W equals to Fs cos theta. Fs cos theta. What is the force? What is the force? It is mg. What is the displacement? L. This is the displacement which is slide down. So L. Okay. What is cos theta? What is cos theta? It is sine 90 degrees. So it would be mgl sine theta. Right. So therefore, what we can see is that work done equals to mgl sine theta. Why sine theta? Because we have seen this one to be cos 90 minus theta, right? So we have seen this one as cos 90 minus theta, right? This one. Yeah. So cos, I can just put it for convenience, cos 90 degrees minus theta. Quite clear? This is theta, this is 90 degree. The component of the force which is acting in this direction as earth is pulling down would be cos 90 minus theta. Just substitute the values, we get it. Plain and simple, quite clear. So we have learned what would be the force on an inclined plane. The last part which is on our video which remains is that what is work due to multiple forces. So just a quick one. I won't take much time because it's already it's a little bit longer video, I understand. So let us draw an object over here, right? And let us say, for example, we have a force acting in this direction, which is F1. We have got a force acting in this direction, which is F2. And we have got another force which is acting in this direction, which is F3, right? And also what we can show you is that when we apply this force, there has been a displacement, right? And it is D, right? So this force, F1 gives you theta 1, F2 gives you theta 2, and displacement has given. I'm not considering the third force which will eventually come. What we have learned right now is that work can be defined as an sum of our integration of F ds. We take the differentiation part, right? So this is the force which is happening, d by displacement. This part is a constant. This part is a constant. So what we can write over here, is that this integration, this ds actually becomes f cos theta. Yeah, because it's a constant. So we get the f cos theta, right? And s is, I can write in this way, from 0 to d, right? It has started from 0 and moved up to d. So it is evaluated from 0 to d. It is called evaluation from 0 to d. Now we will consider what is the work done for F1, F2 and F3. So what, it is quite simple. So so work done for 1, I consider 1 at W1 is equals to F1 d cos theta 1, obviously. This is the displacement which has happened, d cos theta 1. What would be W2? W2 would be F2 d cos theta 2. So it would be d cos theta 2, right? And what would be W3? What would be W3? So W3 is, again, which I showed earlier, it is along this line. You see this particular line. So it is, again, this angle is being formed. So what is this angle? This is 180 degree. What is cos of 180 degree? That is -1. So cos of 180 degrees equals to -1. So eventually the third work done, that is W3, would be minus F3D. It would be minus F3D. So we are almost done with the video. So this one is negative. The reason of it is that cos 180 degree equals to -1. I'm so sorry, I should write it here. Yeah. So cos 180 degree equals to -1. So the work done on the third part, that is the work done W3, equals to minus F3D. Why? Because it is in 180 degrees. Just simply by integrating, and we find out work done 1, work done 2, and work done 3 would be this. This brings to the end of the video. I'm not going to recap again because I have already recapped part by part. So this is an important thing which we have done. Work done in terms of variable force. We have learned what is work done by variable force. We have also learned in the previous parts that what is work done by the gravity, which has pulled things up and down. So that concludes our video. I hope you have liked it. This is something new which you have learned, and just put up your comments if you have to say anything. And that actually brings to the end of the video. 4 topics have been covered. Thank you very much. Have a nice day. Stay safe and stay happy. Goodbye.